In this class, we will be looking into one more example of contraction mapping, and then we will seal the topic and move over to the next topic, that is the matrix and determinants. So, the third example of on contraction mapping that we are looking into this class is that again we will be considering an enzymatic catalytic reaction. Occurring in a CSTR with volume V, flow rate Q, feed concentration of reactant as earlier is CF, and again it is an isothermal irreversible reaction, but the rate constant is different in this problem. The rate expression is different in this problem. The rate expression is given as K1 times C divided by K2 plus K3C plus C square. This is the rate expression. So, at the steady state, you have again we proceed the same way as we have done in the earlier problems. We write down the reactant balance in the CSTR. So, it will be Q times CF minus Q times C minus rate of reactant A times volume is equal to 0. At the steady state, rate of accumulation is 0. This is the net mass that is coming into the system, net mass per unit time going out of the system, the amount of material of reactant that is consumed in the reactant volume per unit time. So, we write down the expression of RA there. So, it becomes plus QCF minus QC minus K1 V times C divided by K2 plus K3C plus C square must be equal to 0. Okay. So, again we non-dimensionalize the governing equation, and after non-dimensionalization we will be getting 1 minus x minus dA times x divided by 1 plus sigma 1 x plus sigma 2 x square is equal to 0. Okay. The rate expression is slightly different. We put it as K2 C square, K1 C, K2 C square plus K3 C plus 1. Okay. So, K2 C square plus K3 C plus 1. So, it is basically 1 plus K3 C plus K2 C square. So, this becomes, if you write down the governing equation, then this becomes QCF. I am just redoing the whole thing for you, minus QC minus K1 VC divided by 1 plus K3C plus K2 C square is equal to 0. We make it non-dimensional. We define x is equal to C by CF. So, divided by Q and CF, this becomes 1 minus C by CF minus K1 V divided by Q, and it is also divided by CF. So, this becomes C by CF. So, the dimensionless concentration, then we make these things also non-dimensional. So, 1 plus K3 C by Cf plus into Cf. So, and this will be K2 Cf square C by Cf square, that will be equal to 0. Put x is equal to C by Cf and Damn-Coulomb number is equal to K1 V over Q. So, in the non-dimensional form, this equation becomes 1 minus x minus Damn-Coulomb times x divided by 1 plus, we call this as sigma 1 x plus this is sigma 2 x square is equal to 0. So, we get the, we will end up in the same equation where sigma 1, the non-dimensional parameter sigma 1 is K3 times Cf and sigma 2 is nothing but K2 times Cf square. Now, we have, so therefore, we have 3 parameters in this system, dA, sigma 1 and sigma 2. All of them are non-dimensional and their definitions are dA, definition of Damn-Coulomb number is K1 V by Q, definition of sigma 1 is K3 times Cf and sigma 2 is K2 times Cf square. So, we must be having, we are looking for a relationship between these 3 parameters dA, sigma 1 and sigma 2, so that there will be existence of a unique steady state to this particular problem. So, this is our governing equation and we are going to cast this equation in the form of x is equal to f(x). So, like the previous problem, we rearrange that equation and we will be getting x 1 plus dA 1 plus sigma 1 x plus sigma 2 x square is equal to 1. So, x 1 plus dA plus sigma 1 x plus sigma 2 x square divided by 1 plus sigma 1 x plus sigma 2 x square, that should be equal to 1. So, x is equal to 1 plus sigma 1 x plus sigma 2 x square divided by 1 plus dA plus sigma 1 x plus sigma 2 x square. So, this is the form x is equal to f(x), where f(x) is given by this expression. So, if we look into the validity of this map f, so let us check the validity of map f. X lying in between 0 and 1, let us put the minimum value of x as 0. So, f at x is equal to 0 becomes 1 divided by 1 plus Damn-Coulomb number, and all these 3 parameters dA, sigma 1 and sigma 2, they lying between the positive real half plane. So, 1 by 1 plus dA is always less than 1, and f evaluated at x is equal to 1 will be 1 plus sigma 1 plus sigma 2 divided by 1 plus sigma 1 plus sigma 2 plus dA. Since dA is a positive real number, so denominator is always greater than numerator. So, this will be always less than 1. So, f(x) is also lying in the domain 0 to 1. So, therefore, choice of this map is appropriate and this map has every quality to be a contraction map. Then we look into the next steps. We have to evaluate f prime x at x is equal to w. We term that as z, then z will be a continuous function of w. Then we look into the z max, maximum value of z, and that has to be less than 1 for this f to be a contraction map. So, let us evaluate f prime x. So, f(x) is equal to 1 plus sigma 1 x plus sigma 2 x square divided by 1 plus dA plus sigma 1 x plus sigma 2 x square. So, f prime x is equal to, we just differentiate it exactly the same way we have done earlier, 2 sigma 2 x divided by 1 plus dA plus sigma 1 x plus sigma 2 x square minus 1 plus sigma 1 x plus sigma 2 x square constant. Then we differentiate this one. So, this will be sigma 1 plus 2 sigma 2 x divided by 1 plus dA plus sigma 1 x plus sigma 2 x square of that. So, we simplify this equation, we take this thing as common, sigma 1 plus 2 sigma 2 x divided by 1 plus dA plus sigma 1 x plus sigma 2 x square. So, this is 1 minus 1 plus sigma 1 x plus sigma 2 x square divided by 1 will be remaining 1 plus dA plus sigma 1 x plus sigma 2 x square bracket close. So, therefore, once you simplify in the numerator only dA will be remaining, all the 3 quantities will be vanished. So, it will be nothing but dA sigma 1 plus 2 sigma 2 x divided by 1 plus dA plus sigma 1 x plus sigma 2 x square of that. So, what is f prime w? So, that is our z. So, z is f prime evaluated at x is equal to w. So, dA sigma 1 plus 2 sigma 2 w divided by 1 plus dA plus sigma 1 w plus sigma 2 w square, then square of that. Now, z is a continuous function of w, where w is a variable lying in the domain of x, that is from 0 to 1. So, we evaluate the z max, maximum value of z. So, maximum value of z will be obtained if we evaluate dz dw and put it to equal to 0. So, if you do that, then this becomes dA times 2 sigma 2 divided by 1 plus dA plus sigma 1 w plus sigma 2 w square of that minus 2 dA sigma 1 plus 2 sigma 2 w, and the differentiation of this becomes sigma 1 plus 2 sigma 2 w. So, this becomes square of that divided by cube of this 1 plus dA plus sigma 1 w plus sigma 2 w square, cube of that should be equal to 0. Now, if one can simplify this whole thing, so dA 2 dA will be cancelled out simply, it will be gone. So, you will be getting sigma 2 multiplied by 1 plus dA plus sigma 1 w plus sigma 2 w square. So, after simplification, and that should be is equal to dA will be cancelled out, this will be remaining sigma 1 plus 2 sigma 2 w square. So, you will be having a relationship between this one. So, so there are two ways to solve this problem. You just look into this problem, and so this is a quadratic in W. So, you can identify that this whole thing 1 plus dA plus sigma 1 w plus sigma 2 w square, that is appearing in the denominator, should be equal to this. So, we can substitute that 1. So, if we do that, so this becomes 1 plus dA plus sigma 1 W plus sigma 2 W square is equal to sigma 1 plus 2 sigma 2 W divided by sigma 2 square of that. So, if we are going to substitute it over here, so Z becomes okay, we will just write in the next one, next page. So, if you look into the expression of Z dA sigma 1 plus 2 sigma 2 W, and we have already obtained 1 plus dA plus sigma 1 W plus sigma 2 W square as sigma 1 plus 2 sigma 2 W square divided by sigma 2. So, therefore, this will be sigma 1 plus 2 sigma 2 W square of that. So, it will be 4 divided by sigma 2 square. So, at the maximum value of Z, this will be dA sigma 2 square divided by sigma 1 plus 2 sigma 2 W to the power 3. Now, we are going to put the value of W where that will be satisfying the earlier equation in here to get an expression of Z maximum. So, therefore, if you go back to the earlier equation, that becomes sigma 2 into 1 plus dA plus sigma 1 W plus sigma 2 W square is equal to sigma 1 plus 2 sigma 2 W square of that. Just open up this square and see what you get. Sigma 2 plus sigma 2 dA plus sigma 1 sigma 2 W plus sigma 2 square W square. So, here you will be getting sigma 1 square plus 4 sigma 1 sigma 2 W plus 4 sigma 2 square W square. So, right. So, you get all these terms on the right hand side. So, W square will be here. So, it will be 3 sigma 2 square W square, sigma 1 sigma 2 will be here. So, it will be plus 3 sigma 1 sigma 2 W and you have plus this is taken care of, this is taken care of, this. So, the rest terms will be sigma 1 square minus sigma 2 minus sigma 2 dA is equal to 0. So, we solve this equation for W, and at this W our Z is maximum. So, W is obtained as minus 3 sigma 1 sigma 2 plus, we should not take the okay, I will come to that later on, plus B square, that is 9 sigma 1 square sigma 2 square minus 4 3 sigma 2 square, 4 into 3 sigma 2 square multiplied by sigma 1 square minus sigma 2 minus sigma 2 dA divided by 6 sigma 2 square. Okay, so, you can further simplify this equation probably to a little bit. So, you will be getting W is equal to minus 3 sigma 1 sigma 2 plus under root 9 sigma 1 square sigma 2 square minus 12 sigma 1 square sigma 2 square minus minus plus. So, 12 sigma 2 cube minus minus plus. So, it will be 12 sigma 2 cube dA divided by 6 sigma 2 square. In fact, we can take 1 sigma 2 square out of this and that will be cancelling out. So, minus 3 sigma 1 plus root over 9 sigma 1 square minus 12 sigma 1 square plus 12 sigma 2 plus 12 sigma 2 dA divided by 6 sigma 2, 1 sigma 2 will be cancelling out. So, this will be 6 sigma 2 minus 3 sigma 1 plus root over 12 sigma 2 1 plus dA multiplied minus 3 sigma 1 square. We should not take the plus minus root here, we should take only the plus sign, minus cannot be the thing, because if you take the minus sign, then W turns out to be minus, and W is ever positive, a fraction lying in the domain 0 to 1. So, therefore, for this value of W, the Z is maximum, and we can put that and see what we get. So, Z max, if you remember, is equal to dA sigma 2 square divided by sigma 1 plus 2 sigma 2 W to the power 3. So, we are going to substitute this value of W here. So, it will be W sigma 2 W sigma 2 is nothing but 1 upon 3, right. So, it will become sigma 2 W is equal to this thing divided by 3. So, you will be having dA sigma 2 square divided by sigma 1 2 sigma 2 W. So, it will be minus 3 sigma plus root over 12 sigma 2 into 1 plus dA minus 3 sigma 1 square. Okay. So, it becomes a bit more complicated. So, we write down that equation once again in a neat compact form. Z max should be is equal to 3 dA sigma 2 square divided by 3 sigma 1 in this equation. 3 sigma 1 and minus 3 sigma 1, it will be simply cancelled out. So, that makes our life simpler. So, this becomes root over 12 sigma 2 into 1 plus dA minus 3 sigma 1 square. So, F to be a contraction map, Z max should be less than 1, and therefore, the whole equation turns out to be 3 dA sigma 2 square divided by a whole thing. So, this should be less than 12 sigma 2 1 plus dA minus 3 sigma 1 square root of that. So, you just square it up. So, it becomes 9 dA square sigma 2 to the power 4 is less than 12 sigma 2 into 1 plus dA minus 3 sigma 1 square. So, therefore, 9 make it more amenable form, dA square sigma 2 to the power 4 plus 3 sigma 1 square should be less than 12 sigma 2 into 1 plus dA. So, this is the equation, this is the inequality between the relationship between the parameters dA sigma 1 and sigma 2 should satisfy in order to have a unique steady state for this particular problem. So, this has become very important if you look into see the complexity of the problems as we have gone up from problem example 1, 2 and 3. We have kept everything constant. In one case, we have assumed a reaction rate expression. In another case, we have changed the reaction rate expression slightly. In the third case, we made the reaction rate expression a more generalized form, and see how the condition for having a unique steady state changes from problem to problem, and for the last problem whatever we have seen, that a rate expression, the generalized rate expression, this is the relationship between the parameters sigma 1, sigma 2 and Damkohler number. So, you have to select Q and Cf, these are the actual operating conditions you are controlling as an operator. On the other hand, these kinetic parameters K1 and K2 and K3, they are being specific, fixed by the rate expression, you do not have much control over them. So, the control you are having over the feed concentration and volumetric flow rate, and these non-dimensional numbers are the combinations of this. So, that this equation have to be satisfied in order to get a unique steady state in your problem. So, therefore, we finish the contraction, we complete the contraction mapping stuff. Next, we go to the next topic, that is the matrix and determinants. Okay. Matrix and determinants are again we will be discussing some of the important properties, and they are extremely important as far as the chemical engineering problems are concerned. They are useful tool to analyze the chemical engineering system. So, as we have seen, we have done in the last few lectures regarding the contraction mapping and the metric spaces, we will try to develop the basic theory and the concepts of matrix and determinants, and how they will be utilized for the chemical engineering systems in real life. We will be looking into couple of examples, and also before that we will be recapitulating some of our the definitions and the properties of basic properties of the matrix and determinants. So, let us do that. Let us look into what is the size of a matrix. Size is written as m into n. So, let us see what m stands for and what n stands for. M stands for number of rows and n stands for number of columns. So, let us look into the various properties. If m is equal to n, then the matrix A, let us say this is size of matrix A, the matrix is a square matrix. If in A 2 rows or columns are interchanged, then determinant changes its sign. Then if next property is that if all rows are interchanged with all columns, that is the ith row becomes ith column, determinant remains same. Okay. So, these are the some of the properties. Then we will look into some more properties of determinants and matrices. The fourth one is that if all elements in a row or a column are multiplied by a scalar alpha, let us say, determinant is also multiplied by alpha. The next property is that if one row or one column, if all elements in one row or one column are 0, then of course determinant is 0. Next property is that if A and B, if two matrices A and B, they are equal, A is equal to B, then number of rows and columns of A should be equal to number of rows, columns of B. So, that is quite obvious. Next one is A transpose. It is, the notation is A superscript T represents transpose of matrix A. This simply says that rows of A are interchanged with columns of A transpose, or the other way around, does not matter. Rows of A are interchanged with columns. So, that becomes a transpose matrix. So, the rows are now becomes columns. So, there are 3 rows, let us say in 3 into 3 matrix, they are become now columns for the columns of a new matrix. The new matrix that is generated by interchanging the rows with the columns is called a transpose matrix. So, therefore, for a if T it represents the transpose matrix superscript, then A I j superscript T should be equal to A j I. So, that is the relationship between the elements of a matrix A and its transpose version. Okay. We go to the next property, that is property number 8. We define a diagonal matrix and remember, diagonal matrix is defined only for a square matrix. What is a diagonal matrix? When off diagonal elements are zeros and on diagonal elements are non-zero. Then the matrix is called a diagonal matrix. So, if you talk about this matrix, let us say A 0 0 0 B 0 0 0 C, then this is a diagonal matrix. If on diagonal elements are 1, then we call it is an identity or unit matrix. On diagonal elements are 1. And 0 elsewhere. So, this will be 1 0 0 0 1 0 0 0 1. So, this is an identity matrix. Okay. So, we look into some more definition of the matrices and determinants. Next property is the matrix multiplication. Let us say two matrices, A which has a size m into n, B which has a size n into p, then A multiplied by B should be is equal to C, which will be having a size m into p. That means, if A has same number of columns that of rows of B, that means number of columns of A should be matching with the number of rows of B, then these two matrices are called conformable matrices. Then A and B are called conformable. Two matrices, if two matrices are conformable, then their multiplication is allowed. Only for conformable matrices multiplication is allowed, otherwise not. Okay. So, if the number of rows of one matrix is equal to number of columns of the other matrix, then these two matrices are multiplicable. So, A which will be having unit elements A I j with the size m into n, B which has elements B I j size n into p should be equal to C, which will be having elements C I j and size m into p. So, C I j can be expressed as summation of A I k multiplied by B k j, where k is equal to 1 to n. So, by following this rule, one can get the elements of the product matrix. We will be getting the elements of the product matrix by following up this rule of the corresponding conformable matrices. Okay. Then we talk about inverse of matrix. If determinant of a matrix A is not equal to 0, then A is called a non-singular matrix. If determinant of matrix A is equal to 0, then A is called a singular matrix. Inverse of matrix exists if A is non-singular. Inverse of A exists for non-singular matrix only. Okay. Next, we look into some more properties. A B inverse is nothing but B inverse A inverse. A B transpose is nothing but B transpose A transpose. Then we talk about the symmetric matrix. If A transpose is equal to A, then A I j is equal to A j I, and we call the resultant matrix A as the symmetric matrix. So, if A transpose is equal to A, then we are talking about a symmetric matrix. That means, rows and the columns, even if they are interchanged, there is no difference between the two, and they are absolutely symmetric matrix. Next one is the orthogonal matrix. If A transpose is equal to A inverse, then we call the matrix A as orthogonal matrix. Then we talk about skew symmetric matrix. A transpose is equal to minus A, then it is a skew symmetric matrix. If you remember the definition of a symmetric matrix, A transpose is equal to A, and for the skew symmetric matrix, A transpose is equal to minus A. So, let us look into the matrix of. So, these are the basic definitions and properties of matrices and determinants. Then let us look into any matrix operation. Okay. Let us say A x is equal to y, where A is a m cross n matrix, whereas x is n cross 1 vector. Then y is nothing but m cross 1 vector. So, this vector is basically nothing but a special matrix where the number of columns is 1. So, when you talk about A and x, see number of columns is equal to number of rows of this number of columns of this matrix and number of rows of this vector. So, they are conformable. So, their product is, if their multiplication is allowed, then you will be getting another vector of size m cross 1. So, it becomes a vector, it no longer becomes a matrix. So, it becomes a special form of matrix known as the vector. So, what is A? It is like y is equal to f x. So, A is an operator, matrix is an operator it operates on a vector of size n and maps it in a vector of size m. So, matrix is an operator that operates on a vector of size n and maps it on another vector of size m. So, matrix is nothing but an operator and it is a map, it is nothing but an operator or a map. So, A maps n dimensional vector into m dimensional vector. So, it maps n dimensional space into m dimensional space. So, in a short form we can write A is a map which basically takes up the n dimensional map into m dimensional map in real space. Okay. So, consider another property of the vectors. Consider the two vectors x and y, both belong to n dimensional real space. Okay. So, both are n dimensional vectors. So, y is nothing but y 1, y 2 up to y n, and x is x 1, x 2 up to x n. Then y, what is y transpose? Y transpose is y 1, y 2, y 3 up to y n. The column becomes row in case of transpose. Then it becomes, it has a size n into 1. Okay. It will be there are n number of rows. So, this will becomes n into 1 and this will be a size of 1 into n. So, this is y transpose and x is also having a size n number of rows and 1 column. So, n into 1. So, y transpose and x, they are conformable. So, y inner product of so y transpose and x are conformable and matrix multiplication is allowed. So, if you multiply y transpose and x, then it becomes summation of x I y I. So, if you take the inner product of y and x, if you remember the definition of inner product of vectors, we take up the corresponding elements of the vectors, multiply them and add them up. So, that also becomes multiplication summation of x I y I. So, therefore, inner product of y and x is nothing but y transpose multiplied by x. So, this is very important relationship and we will be utilizing this relationship quite often in our as we proceed in our course. So, inner product of y and x should be is equal to multiplication of y transpose and x. Okay. So, we have looked into several properties of matrices and vectors and looked into some special form, special relationship of the transpose matrix and the operators like the how they will be connected to the inner product space, and then we will be able to position to move on further for an eigenvalue problem, and we will see various theorems those are valid for the eigenvalue problems and how eigenvalue problems are quite important in various chemical engineering applications, and we can solve so many of chemical engineering problems by elegant eigenvalue eigenvector approach. So, next we talk about to the move forward with the eigenvalue problem. If the form of the matrix A x is equal to lambda x, where lambda is a scalar multiplier, so if that is the form, that means A is a matrix of size n into n. So, we are talking about a square matrix and this is a vector of size n into 1. So, these two are conformable. So, it will be returning a vector n into 1. So, n into n matrix, it will be operating on a vector n into 1 matrix, number of rows and number of columns are identical, then it will be returning a vector. So, they are conformable and multiplication is allowed, and they will be returning the vector of size n into 1. So, this is a vector of size n into 1 and this is a scalar. If we write an equation like this, then we call this problem an eigenvalue problem. So, if we write different elements of a matrix A11, A12, A13 up to A1n, A21, A22, A23 up to A2n, then this will be AN1, AN2, AN3 up to ANn. Multiplied by, we write the different elements of x vector x1, x2 up to xn is equal to lambda times x1, x2 up to xn. Then we just subtract, we just bring the right hand side into the left hand side and write in the form of x1, x2, x1. So, we can write it as A11 minus lambda A12 up to A1n, A21, A22 minus lambda up to A2n, like that AN1, AN2 up to ANn minus lambda. This becomes same as x1, x2, x3 up to xn. This is equal to 0. So, in a compact form, we can write down that A minus lambda I, that is the identity matrix, multiplied by x should be equal to 0. So, the form, so therefore, the form A x is equal to lambda x is called an eigenvalue problem. And we will see in the next class how the eigenvalue problems are so important for the chemical engineering applications and what are the different important properties of the eigenvalue problem which we will be exploiting to solve the chemical engineering problems. Thank you for your kind attention.